Across a span of 93 billion light-years, a fabric of spacetime, woven from dimensions we perceive and others we do not, stretches under an unseen and unrelenting tension. This is the observable universe, a finite bubble of knowledge within a potentially infinite expanse, and its fundamental state is one of perpetual expansion. Every second, the gulf between distant galaxy clusters widens by a measure precisely quantified, a velocity of approximately 73 km per second for every megaparsec of separation, a value known as the Hubble constant. This single, hard-won number is not merely a descriptor of cosmic motion, it is a prophecy, a key that unlocks the story of the universe's ultimate fate. This expansion is not the coasting momentum of an ancient explosion, but an accelerating process, driven by a pervasive, anti-gravitational influence woven into the vacuum of space itself. We call this influence dark energy, a name that signifies the profound depth of our ignorance, for it constitutes nearly 70% of the universe's total energy density, yet its origin and nature remain one of the deepest mysteries in all of science. It is a quiet, persistent pressure, a cosmological constant that pushes where gravity pulls, ensuring that the grand assembly of matter, the great cosmic web of galaxies, is destined not for collapse but for an inexorable, ever-accelerating isolation. The faint, uniform glow of microwave radiation that permeates all of space, the cosmic microwave background, is the fading echo of a hotter, denser beginning, a time when the entire universe was a seething plasma, smaller than a single atom is today. From that primordial fire, gravity sculpted the first stars, the first galaxies, and the intricate, sprawling structures we now inhabit. But the same force that built these cosmic cities is now losing its war against the pervasive emptiness, against the patient, unyielding push of dark energy, which has become the dominant actor on the cosmic stage. The future, therefore, is written not in the language of gravitational collapse, but in the language of dilution and decay, a slow unwinding of all that has been so carefully constructed over 13.8 billion years. Over trillions of years, a profound and irreversible quiet will descend upon the cosmos. The stelliferous era, the age of stars, the only age the universe has ever known, will draw to a close. The vast, cold reservoirs of interstellar hydrogen and helium gas, the raw material from which stars are forged, will be exhausted. Within the spiral arms of galaxies like our own Milky Way, the brilliant, short-lived blue giant stars have already long since vanished, their violent supernova deaths seeding the void with the heavy elements necessary for life. Following them into oblivion are the sun-like yellow dwarfs, which swell into red giants before puffing away their outer layers to leave behind the cooling, crystalline embers of white dwarfs. The last beacons of light in this darkening universe will be the red dwarfs, the most common and longest-lived of all stars. These dim, frugal furnaces sip their hydrogen fuel so slowly that their lifespans can extend for trillions of years, far longer than the current age of the universe. For a time, they will be the only light, casting a faint, crimson glow on the frozen worlds that orbit them. But even their fuel is finite. One by one, they too will flicker out, their fusion ceasing, their light fading until they become inert spheres of helium, slowly cooling in the eternal night. The process of star formation, the engine of galactic life, will have sputtered to a complete halt. Galaxies, once radiant whirlpools of light and gas, will become ghostly collections of stellar remnants. The collision and merger of our own Milky Way with the Andromeda Galaxy, a process beginning in a mere 4 billion years, will trigger a final, spectacular burst of star formation, a brief, luminous reprieve before the permanent darkness. The resulting supergalaxy, sometimes dubbed Milkomeda, will then coast into the deep future as a silent, sprawling graveyard, a dark island of matter in an ever-expanding, ever-emptying sea. The night sky, viewed from any remaining planetary body, will be almost perfectly black, the distant, receding galaxies having been carried by the expansion of space beyond the cosmic event horizon, their light no longer able to reach us, rendering them forever invisible and unknowable. As the last red dwarf cools to a temperature indistinguishable from the cosmic background, the universe enters the degenerate era, a period whose timeline dwarfs all that came before. The cosmos is now populated entirely by the dead, by the compact, collapsed remnants of once mighty stars. These are the white dwarfs, planet-sized spheres of electron-degenerate matter, composed of carbon and oxygen nuclei locked in a crystalline lattice, holding the mass of a sun in a volume no larger than the Earth. Over unimaginable timescales, these objects will continue to radiate away their residual heat, their faint glow shifting from white to yellow, to red, and finally, to nothing, becoming black dwarfs, cold, dark, and utterly inert. Alongside them drift the neutron stars, the even more extreme relics of supernova explosions. These are city-sized spheres of neutron-degenerate matter, so dense that a single teaspoon of their substance would outweigh a mountain. They are cosmic fossils, spinning silently in the dark, their powerful magnetic fields having long ago decayed. The third and most dominant class of objects in this era are the black holes, both the stellar mass varieties left over from the most massive stars and the supermassive behemoths that lurk at the cores of every galaxy, millions or billions of times the mass of our Sun. These gravitational tyrants are the new centers of the universe, their immense gravity slowly and patiently shaping the dynamics of the dead galaxies around them. Over timescales of quintillions of years, the stable orbits of the remaining black dwarfs and neutron stars will be disrupted through a process of violent relaxation. Some will be flung out of the galaxy entirely, ejected into the lonely, ever-widening intergalactic void. Others will spiral inward, their orbital energy radiated away as gravitational waves, until they are consumed by the central supermassive black hole, adding to its mass and its dominance. The universe becomes a place of immense voids punctuated by dark, gravitationally bound archipelagos of stellar corpses, themselves slowly dissolving as their constituent parts are either swallowed by black holes or exiled into the endless emptiness between the galaxies. Within these cooling, decaying structures, on a timescale so vast it renders the age of the universe infinitesimal, a far more fundamental process of dissolution may begin. This is the era of proton decay, a hypothetical but deeply compelling prediction of many grand unified theories, which seek to merge the strong, weak, and electromagnetic forces into a single, primordial interaction. According to these theories, the proton, the cornerstone of baryonic matter, is not truly stable. It is merely extraordinarily long-lived. Over an average timescale estimated to be on the order of 10 to the power of 36 years, a proton is predicted to spontaneously decay into lighter subatomic particles, such as a positron and a neutral pion, which itself then decays into a pair of high-energy photons. For a single proton, this is an event of inconceivable rarity. But in a universe still filled with the protons locked away inside black dwarfs and neutron stars, this decay, however slow, becomes a continuous, inexorable process of dissolution. The very substance of matter begins to unravel. The crystalline structures of the black dwarfs, the dense neutronium of the neutron stars, will slowly evaporate, not through heat, but through the fundamental instability of their own constituents. A black dwarf, once a sun, will slowly transform into a diffuse cloud of radiation and leptons, electrons, positrons, and neutrinos. It will not burn out, it will simply dissolve, its mass converting entirely into energy over a span of time that is a 1 followed by 37 zeros. Even the most resilient structures, the neutron stars, will succumb, their tightly packed neutrons decaying back into protons and electrons, which then meet their own fate, until the entire object has vanished into a whisper of gamma rays and ghostly neutrinos. If protons do decay, then the degenerate era is not a permanent state, but a temporary one. It marks the long, slow, final death of matter itself, the erasure of every complex structure built since the Big Bang. The universe becomes an almost featureless expanse, a thin, cold soup of photons, neutrinos, and other fundamental particles, with the very concept of a place or an object losing its meaning. Should the proton prove to be absolutely stable, defying the predictions of our most ambitious theories, another, even slower process of annihilation awaits. But even if matter does dissolve as predicted, one class of object persists long after the last black dwarf has evaporated, the black holes. They are the ultimate survivors, the final repositories of structure and complexity in the cosmos. For a time that beggars all imagination, the universe enters the black hole era. Having consumed the remnants of their host galaxies, the supermassive black holes at the galactic cores are the last organized systems in existence. The universe is, for all intents and purposes, a vacuum populated only by these isolated, gravitationally dominant points of infinite density. For a very long time, it was believed that they were eternal prisons, from which nothing, not even light, could escape. But this picture was proven incomplete. Through the lens of quantum field theory, Stephen Hawking demonstrated that black holes are not entirely black. Due to quantum effects near their event horizons, they emit a faint thermal glow, a phenomenon now known as Hawking radiation. A black hole is not a static object but one that is slowly, painstakingly, evaporating. The process is fantastically inefficient. The temperature of this radiation is inversely proportional to the black hole's mass, meaning that larger black holes are colder and evaporate more slowly. A black hole with the mass of our Sun would take an estimated 10 to the power of 67 years to evaporate completely. The supermassive black holes, weighing billions of solar masses, will endure for incomprehensible durations, perhaps as long as a Google years, 10 to the power of 100. For this immense span of cosmic history, they will be the only dynamic actors, their slow evaporation the only meaningful process occurring anywhere in the universe. As they shed mass, they grow hotter and radiate faster, leading to a runaway process that culminates in a final, brilliant flash of high-energy gamma rays as the last fraction of their mass converts into energy in an instant. One by one, from the smallest to the largest, the last black holes will disappear, leaving nothing behind. After the final, explosive evaporation of the last supermassive black hole, the universe enters its ultimate and seemingly final state, the dark era. This is the era of heat death. The cosmos has reached a state of maximum entropy, a near-perfect equilibrium from which no useful work or complex process can ever arise. It is a vast, cold, and achingly empty place, expanding eternally under the gentle, persistent influence of dark energy. The only remaining constituents are a diffuse, homogeneous bath of fundamental particles, low-energy photons, neutrinos, and a scattered population of electrons and positrons, all separated by immense, ever-growing distances. The temperature of this universe will have approached, but never quite reached, absolute zero. There are no more stars, no more galaxies, no more black holes, no more matter as we know it. All structure, all information, all complexity has been erased. Time, in a meaningful, thermodynamic sense, loses its arrow. With no irreversible processes left to occur, no stars to burn, no black holes to evaporate, the distinction between past, present, and future becomes meaningless. It is a universe in stasis. The question of whether such a universe exists becomes a philosophical one. It has volume, it contains energy, and it is governed by physical laws, but it is a universe where nothing ever happens. All the grand celestial dynamics, all the intricate chemistry of life, all the history of consciousness and discovery, has diluted into a featureless, uniform cold. This scenario, the Big Freeze, is the most straightforward extrapolation of our current cosmological observations. It is not an end in the sense of a sudden annihilation, but an end in the sense of infinite, unchanging silence, a final, stable state from which there is no escape and in which the story of the cosmos has, for all practical purposes, concluded. The universe does not cease to be, but it ceases to matter. Yet, even in this state of near-absolute nothingness, the strange and counterintuitive laws of quantum mechanics may offer a final, ghostly postscript. The vacuum of the dark era is not truly empty. It is a roiling sea of quantum fluctuations, a place where pairs of virtual particles and antiparticles spontaneously pop into existence from borrowed energy before annihilating each other in a flash, all in accordance with the Heisenberg uncertainty principle. Over ordinary timescales, these fluctuations are microscopic and fleeting. But over the truly stupendous timescales of the dark era, the improbable becomes the inevitable. Given an almost infinite amount of time, a random quantum fluctuation could, in principle, be large enough to create something new. It is theoretically possible, though with a probability so low it is functionally zero, for the particles in the void to randomly arrange themselves into a complex structure. This leads to the bizarre and unsettling paradox of the Boltzmann brain, the idea that over an infinite timeline, it is statistically more likely for a fully formed, conscious brain to spontaneously fluctuate into existence, complete with false memories of a past that never happened, than it is for an entire new, low-entropy universe like our own to emerge. This thought experiment serves to highlight the profound conceptual difficulties we face when applying our physics to such extreme and unfamiliar regimes. A more plausible, though still highly speculative, quantum event would be for the entire universe to undergo a process of quantum tunneling, transitioning from its high-entropy, low-energy vacuum state to a new, different vacuum state, potentially triggering a new inflationary phase and birthing a new cosmos with potentially different physical laws. In this vision, the heat death is not a permanent end, but merely a metastable state, a cosmic pause of unimaginable length before the universe reinvents itself through a random quantum leap. Existence would not stop, but it would be subject to a cosmic lottery on a timescale that makes the evaporation of a black hole seem like the blink of an eye. This entire timeline of slow decay and potential quantum rebirth, however, is predicated on the assumption that the nature of dark energy, the mysterious driver of cosmic acceleration, remains constant over time. Our current measurements are consistent with it being a cosmological constant, a fixed energy density of the vacuum. But what if it is not constant? What if it is a dynamic field, something cosmologists call quintessence, that can change over time? One particularly dramatic possibility is a hypothetical form of dark energy known as phantom energy. Unlike a cosmological constant, the energy density of phantom energy would increase as the universe expands. This would create a runaway feedback loop, causing the expansion of space to accelerate at a truly exponential rate. The consequences of such a scenario, known as the Big Rip, would be catastrophic and final. The timeline of dissolution would be violently compressed. Trillions of years of slow decay would be replaced by a few billion years of escalating destruction. In the final phase of a Big Rip, the accelerating expansion would first overcome the gravitational pull between galaxies, tearing the cosmic web apart and isolating every galaxy. As the expansion rate continued to increase, it would then become strong enough to overcome the gravity holding individual galaxies together, unbinding stars and sending them flying into the void. The process would continue to cascade down to smaller scales. With only years to go, the expansion would be powerful enough to overwhelm the gravity-holding solar systems together, stripping planets from their stars. In the final minutes, stars and planets themselves would be pulled apart. In the last fraction of a second, the fabric of space would expand so violently that it would overcome the electromagnetic force holding atoms together, and finally, the strong nuclear force itself. Every atom, every proton and neutron, would be ripped into its constituent quarks and gluons. The scale factor of the universe would become infinite in a finite amount of time, and the very fabric of spacetime would be torn asunder. This is not an end by cooling or decay, but a true and total annihilation, where every structure is destroyed and the universe itself ceases to exist in any recognizable physical sense. A third, and perhaps more hopeful, possibility exists, one that pulls back from the brink of either infinite cold or infinite violence. This scenario hinges on the idea that dark energy is not a constant, nor a phantom menace, but a temporary phenomenon that will eventually weaken, or even reverse its sign. It is also the fate predicted if the overall geometry of the universe is not flat or open, but closed, like the surface of a sphere, containing enough mass and energy to eventually halt its own expansion. In this case, gravity, the patient sculptor of the cosmos, would ultimately win its long war against expansion. After billions or trillions of years of accelerating outward, the expansion would begin to slow. The most distant galaxies, which had been receding from us at ever-increasing speeds, would appear to slow down, halt their retreat, and then begin to move toward us. The universe would have reached its maximum size and entered a contracting phase. This would be the beginning of the Big Crunch. The timeline of the universe would play out in reverse. Galaxies, instead of flying apart, would rush toward one another, their light blue shifted as they approached. The cosmos would grow hotter and denser. The cosmic microwave background radiation, which had cooled to near absolute zero, would be compressed and heated, eventually becoming a searing bath of visible light, then X-rays, and then gamma rays, a cosmic microwave foreground that would incinerate any remaining structures. In the final moments, the universe would become a furiously hot and dense plasma, similar to the state it was in just moments after the Big Bang. As galaxies merged and stars were torn apart, black holes would collide and coalesce, growing at a ferocious rate until the entire contracting universe was essentially a single, all-consuming black hole. According to classical general relativity, this collapse would continue until all matter and energy were crushed into a singularity of infinite density and temperature, a point where space and time themselves cease to exist. However, many cosmologists speculate that quantum gravity effects, which would become dominant at such extreme energies, would intervene to prevent the formation of a true singularity. Instead, the universe would bounce, rebounding from the point of maximum compression to begin a new cycle of expansion, a new Big Bang. In this cyclic model, existence does not have a final end, but is instead part of an eternal series of rebirths, with each universe rising from the ashes of the one before. Between these three profoundly divergent paths, the cold, eternal equilibrium of the heat-death, the violent, finite tearing of the Big Rip, and the cyclical rebirth of the Big Bounce, lies the absolute boundary of our current scientific knowledge. Each scenario is a logical consequence of a different assumption about the fundamental nature of the universe's most mysterious components, the precise character of dark energy and the ultimate laws of quantum gravity. The universe's eventual fate is not a settled question, but an active, vibrant area of theoretical and observational research. The answer lies hidden in the precise measurement of the cosmic expansion rate, in the distribution of galaxies on the largest scales, and in the search for a unified theory that can describe both the quantum and the cosmic. What is clear is that the universe we inhabit is a temporary phase. The present era, with its brilliant stars, complex chemistry, and the fragile possibility of life, is but a fleeting moment between a fiery beginning and an end of unimaginable scale and strangeness. The question of whether the universe will stop existing is therefore a matter of definition. In the heat-death, physical process ceases, but the stage remains. In the Big Rip, the stage itself is destroyed. In the Big Bounce, the play ends, but is destined to be performed again, perhaps with a different script. The cosmos is not a static object but a process, and its end, whatever form it takes, is the ultimate expression of the physical laws that have governed it from its first instant. The search for this final answer is not an act of morbid curiosity, but a continuation of the same fundamental drive to understand our place in the cosmos, to read the story written in the light of distant stars, and to comprehend the full, magnificent, and terrifying scope of what it means for a universe to be.